We know that permanent magnets or bar magnets create magnetic fields. Another way that magnetic fields are created is through moving charge. Currents are moving charges, and there are three places that we see moving charges appear in our study of magnetism. The first is in current-carrying wires, shown here. For such a situation, the moving charge in the wire creates circular loops of magnetic field centered around the wire. To find the direction of this magnetic field, we use our right-hand rule for wires, shown here in the diagram, and the magnitude of this magnetic field is given by this equation, where mu naught is a constant, I is the current, 2 pi is a constant, and r is the distance away from the wire. You can also think of this as the radius of each loop of magnetic field. The second place where we see moving charge is in current-carrying loops. This is a loop of wire that has some current I, and we can find the direction of the magnetic field produced by this loop using our right-hand rule for loops, shown here. And what happens with these loops is they actually act like little bar magnets, because if we look at the magnetic field here in purple caused by the current going around in a loop, what we see is on this side of the loop, we see magnetic field lines emerging from the loop, as if it's a north pole. Whereas on the left side over here, we have magnetic field lines going into the loop, as if it's a south pole. The magnitude of this magnetic field at the exact center of the loop is given by this equation, where mu naught is a constant, I is the current, 2 is a constant, and r is the radius of the loop. A third place where we see moving charge creating magnetic fields is in a solenoid. A solenoid can be thought of as just a collection of current loops that we saw before, where the same current though flows through each of the loops and they're connected because it's just a single wire. To find the direction of the magnetic field produced by the solenoid on the inside of the loops, again we use our right-hand rule for loops, shown in this diagram, and then the magnitude of the magnetic field inside the solenoid is given by this equation, where mu naught is a constant, n is the number of loops, which for this solenoid would be 1, 2, 3, 4, 5, I is the current, and L is the length of the solenoid. Like what we saw for our current-carrying loops, solenoids also act like bar magnets, where on this side of the solenoid, where the magnetic field emerges, we have a north pole, and on this side we have a south pole. The magnetic field inside a solenoid is constant, and so the actual magnitude of the magnetic field at each point on the inside is going to be given by this equation, and the magnetic field on the outside is 0.